Hello everyone, my name is Yini Wang. Uh, we are Team C Star, and I'm responsible for automation, data analysis, and video processing.
I'm Ranmo. I'm responsible for design, video processing, and testing. The purpose of our project is to help Professor Oakley in marine science to study some marine species called ostracods. They are like very small shrimps, and they are interesting because they can generate beautiful light when they move or communicate with each other. Besides, ostracods have large diversity and their evolution is very fast. So study of ostracods is greatly valuable in marine science. Our project C-Star is based on a previous ECE project, WALL-E, which is made for Oakley's lab as well. We need to record both videos of the bioluminescence from ostracods and the light levels of the bioluminescence with extreme precision. After that, we need to post-process and analyze the videos to get the data for further study. The previous team had finished the first part, and their equipment has two Latte cameras, which can record the videos underwater. So our work focuses on the following two aims. Now, there is no such existed device for this specific purpose, so we must design it with basic elements.
And our solution is to use PMT to record overall light levels. After we collect data from water cameras, we will post-process and analyze the recorded videos in the following order. We will start with denoising, RGB conversion, Ostracods detection, temporal signal identification, 3D coordinate extraction, stereo-calibration, frame matching, and stereo-rectification.
This is the block diagram of C-Star. We added the PMT and the Latte Panda computer beside the original WALL-E device. Both the scene of the water cameras and the screen of the Latte Panda computer can be shown on a waterproof monitor, so it is easy to operate underwater. This is the PMT we use to record light levels. It is an extremely sensitive detector of light that it can count the number of photons that enter in its round window. It is essential for studying ostracods because the light level change can accurately tell the researchers the activities of ostracods. We chose this type because it's high quality, small size, and USB interface. So we can use the single board computer to supply its power and control it. For running the software controlling the PMT, we use the Latte Panda single board computer. We chose it because it has Windows 10 operating system, which is required by the PMT software, and its size is small, about 7 centimeters by 8 centimeters. Besides, it only needs 5 volt at 2 amp power supply, so we can use normal battery as power supply underwater.
We used this software called Hamamatsu to control the PMT. As you can see in the screenshot, users have to input the gate time and gate number and search the device manually. However, it's impossible to do that when PMT is in a waterproof casing underwater. So we wrote a script to control the software and have it complete the process automatically after users preset the configurations. And here is the result of PMT, and it shows how many photons passed through the PMT every 10 milliseconds. So when there is an increase of number of photons, it means ostracods flashed.
As we mentioned before, our PMT needs to work underwater, so we designed and made a transparent waterproof casing. It is made by 2 centimeters thick acrylic material, so it can also work under great water pressure. Then we designed the casing peripherals for fixing the Latte Panda computer and the PMT in the casing. These are the models of the peripherals for 3D printing. Although we didn't get a chance to print them out due to the coronavirus, It's easy for Professor Oakley to print them out in his lab later. Besides the PMT automation, we have some jobs to do for the videos recorded by the water cameras in Wally. The bioluminescence from Ostracods is wonderful like this image, but our cameras cannot take the scene like this. The reality is like this image. The frames of videos are very noisy, and the white point like the circled one is the light from Ostracods. Therefore, we have to finish the video post-processing before further analysis. The first step is denoising. We roughly denoise the video by judging the grayscale value and eliminate most noises at the beginning, so we can get the resulted video like the right one. However, this is not enough because some noises have relatively high brightness, like the one shown in this example. So we still need to denoise the video by looking at other criteria. Therefore, we judge the light and the duration of the light and the max brightness and brightness change of a small part of the video in one time period. In this way, we can eliminate all noises and keep only the real signals.
In order to restore the signals, after denoising, we converted the signals from grayscale to RGB. And this is part of the video after denoising and RGB conversion. As you can see in the video, the signal occurred a few times. And our program can find all the signals occurred in the video and take a screenshot of each signal's brightest frame. All the frames will be saved to local for future analysis, and return a graph to show the relationship between the light levels and time. Also, the program will find signals XY coordinates and then calculate the 3D coordinates correspondingly. With the 3D coordinates, it's possible to visualize Ostracods movements. Also, because we are using fisheye cameras, so the objects and the signals are distorted in the videos. Therefore, after we finish the 3D coordinates extraction, we need to do the stereo calibration. We first calibrate the checkerboard and generate the map and apply the map to the video. Then, because of the system errors, the left and right cameras will now start recording at the same time. Therefore, the two video frames are unmatched. In order to match the frames, based on checkerboard movements, we find a turning point of the checkerboard in each video and then cut the videos. For example, if the left video is 12 frames ahead of the right video, we will cut 12 frames at the beginning of the left video and cut 12 frames at the end of the right video. In this way, two videos will be frame matched and have the same length.
And last, we did stereo-rectification to the two videos. This step crops the two videos so that the signals in the left and right videos have the same y-axis. In this way, the analysis for the coordinates will become much simpler. After this, we can get the final resulted videos. The following is our demo video. This demo video shows the functions of our video post-processing. The first step is denoising. And the result is clear, so we often use this result in analysis. This is RGB conversion. This step is mostly for demo the real color of Ostracods, and it is better to apply this for videos containing multiple Ostracods. So the Ostracods will become more clear and colorful. Then this is the stereo calibration. You can see that the lines of the chessboard are straighter in the results. Finally, we use frame matching and Stereo-Rectification to make the left and right video have same time and y-axis offset. Through the whole project, we've finished much work for both the PMT and the videos. We first add the PMT part on the device for studying Ostracods, including PMT automation and casing design. Then we completed a set of video post-processing like denoising, RGB conversion, stereo calibration, frame matching, and stereo-rectification. We also did some analysis for the videos, like detecting the Ostracods and calculating the 3D coordinates of the Ostracods.
At the end, we want to thank Oakley Lab and Professor Iskafli, Kyle and Adi for their help and support throughout the whole year. Thank you very much, and we are open to questions.
So if you had some more time to work on this project, is there any more features you would have liked to implement?
Sure, because there are different kinds of Ostracods. So if we have more time, we'd like to do related to machine learning to detect which kind of Ostracode it is.